Well, thank you. Thank you all. I know I stand in a precarious position now between you and lunch, so I'll try to be nice and go fast through the slides. There were some interesting discussions here about the sensors and the models and the other means that we use to monitor the soil moisture and predict it. And it reminded me of how complicated the soil moisture is. Yet we talk about water as one of the major drivers of a lot of processes. But when it comes to the soil moisture, somehow the water slows down to a crawl, and it becomes very challenging then for us to measure it, especially when it comes to the extreme of it, the drought. So we have been struggling with this point as far as how to connect the measurements at the point what the sensor sees and how to connect that to another landscape or upscale it to a landscape or to a scale that makes sense or sort of it's more user-friendly for people that can make decisions. Because some of the models can look at a 30-kilometer view and they do great predictions that are mostly driven by precipitation, like someone said, and soils at some point are not that important. Well, it becomes noise. And it reminded me of some of the great articles that were written in the past about the stochastic and deterministic line. So we're walking a line now between stochastic and deterministic, depending on where we are on the scale. And that sort of set the background for this, because just to keep that in mind when we talk about sensors and models and what they're seeing as far as the soil moisture. So as I said, there are multiple challenges when it comes to the soil moisture. You all are familiar with it. I'm not going to mention them. You can just see them, but this is pretty much, preaching to the choir. So that's why we come into sometimes we feel like there's got to be another way to kind of connect the sensor or make sense of what we see and connect these sensors or other observations to a scale that makes sense. And it's a scale that we make decisions. That's where the sort of most of the decisions are being made by farmers. You mentioned the agriculture use. That's where the decisions are being made. Those maps that come from the global scale, those are for regional planning and other things, but the local scale is the one that a lot of people use. So that becomes sort of important and a focal point of our research. And the way to get to that is to use distributed models, fully distributed hydrological models. Now, that being said, doesn't mean that they are full, they are proof and they're good. They have their own, challenges and bags of tricks, so to speak. And these are some of the challenges that we find when it comes to running, distributed models as a way to sort of a bridge that that gap. And I'll say careful, I use with cautious the word bridge because there are multiple bridges, because you're dealing with sensors, point, models, global, surface, with depth, and everything in between. So there are multiple bridges. So models or sensors or any other model are not one solution. There is a multiple solutions, an ensemble of models to get to the accurate predictions. So here is a good example of how challenging it is to drive to distribute, to run these distributed models. As you can see, they are data-driven, as a lot of people here recognize. And for us, it's kind of important because most of these parameters that are input in the model relate very well to the landscape scale. You can get this information to a very sort of relatively good as an input to the model. And what we focus on the output is the soil moisture. Most of these models were derived for stream flow, which is to the left, but we now are using it for something that this model was never intended to, for soil moisture, and that therefore it gives some challenges. So here's a location where we applied this. It's one of the LTRs of ARS networks. It's got a lot of data. It's in Pullman, Washington. These are some of the characteristics of the site. It's got a good relief, so the model can apply. The topography is one of the major drivers. Soils are relatively uniform, but there are some discontinuities that we have noticed. And the precipitation, it's really driven by monsoon season. You have dry seasons in the fall and in the winter, early fall and early spring, but then you have some wet seasons in between. So here's what we see. These are the sensors, the average sensors, and the model. And as you can see, there are some sort of trends that you can observe from this. First of all, when you look into the surface, it seems that the variability between the sensor is much less compared to the depth. And also, the models seem to be more tight compared to the variability in the sensor, which is understandable. I think this is not news to the group here. You have seen this everywhere. And as you go with depth, the uncertainty or the variability between sensors, it widens. This is one observation. The other one is that it varies along the season. If you look into the beginning in the fall, it seems to like struggle. All this are doing the same thing, whether the model or a sensor, they're going flat. So there's nothing there, probably because it's very dry. So both model and the sensor are struggling, and then it looks like there's nothing there. And it happens the same as you go towards the drought season in the summer. You start to see they start to drift apart. They agree, but they're drifting apart. They're seeing different things, or not. They're not even close to each other. And if you look into this, if I wouldn't have shown you that, if you look into this and just look at the R squares, then one can think, oh, this is pretty good, right? You can see that you have some season variability, and you can see that for the summer and for the fall, they're performing better. But these are some of the late summer and the early fall where it's dry. And so, yes, the R squares are looking great, but they're not doing anything. They're not informing anything they're not responding to anything. But during the transition, they seem to be more in agreement. But then you can see now that the R squares are way below, which means that they are looking at different processes, and they are limited by what their what the initial conditions were for setting them up for the sensors and for the models. So again, the same thing for the landscape, and the same thing with depth, as I was explained. So we got two sensors that we run the dynamic to see the same problem or the same issues. And here is a demonstration of what it looks as far as the soil moisture and what the sensors are saying. And then we compare that with SMAP. And you can see that the models in general and the SMAP respond to the weather forcing, but the sensors somehow do not respond to that. And probably it's because their footprint or what they're seeing is very different from what the model is seeing and the assumptions they're making. So again, this is kind of a summary of what I just tried to describe. But again, it's not to say that sensors are wrong or the models are wrong or they're right. Everything, it depends, and it's just the scale dependent and season. So I think these are kind of the two main conclusions, and I'm done. Any questions? Later, right?